All right. So in the last few classes, we are discussing about the band structure of 3D crystal, and we specially talked about three semiconductors: silicon, germanium, and gallium arsenide, and other semiconductors that is used mostly for electronic devices like indium arsenide, indium antimonide, indium gallium arsenide. So their band structures are similar to these three semiconductors that we have discussed. So we talked about energy bands, and we have discussed that there are energy states that electrons can occupy in a semiconductor. Um, so here I have taken example of silicon because silicon is the most widely used semiconductor, and we will spend most of our time in this course with silicon. Um, so if you look at silicon, so this is basically the silicon is an anisotropic material. It's a 3D crystal. So we have mostly the three directions: 001, 100, and 111. And so in the left hand side here, right? So this is the typical EK diagram of silicon. And so basically, as we discussed in the last class, so if you look at the x-axis, there are 3 points: gamma point, x point, and L point. So these points are coming from the Brillouin zone, and gamma point is the center of the Brillouin zone, and x point is towards 100 direction, and L point is towards 111 direction. And we also discussed that the bottom of the conduction band. So basically, here this is only plots the valence and conduction band, right? So because basically we are interested in the valence and conduction band. Valence band is the maximum energy where you can find electrons at 0 degree Kelvin, right? Means absolute zero temperature. So electrons mostly go from valence band to conduction band, and the electrons in the conduction band, they are means used in the transport, right? So um, so here if you see, so we discussed also in the last class, the minima of the maxima of the valence band is at the gamma point at the center of the Brillouin zone. So this is the k equal to 0 point, right? So center of the Brillouin zone is k equal to 0, right? And your gamma point is defined at center of the Brillouin zone. And but um, the maxima of the valence band happens at gamma point, and the minima of conduction band, it is in the 100 direction, 100 phase. So this is not at k equal to 0. So this is this is at some k point to in 100 direction, right? Mostly very close to the x point, right? So so that's the reason, since at k equal to 0, means since valence band maxima and conduction band minima, they are not at the same k. So we define silicon as an indirect band gap semiconductor, right? If an electron has to go from valence band to conduction band, so it needs energy as well as some momentum, right? Because if the electrons has to go from the max uh, valence band maxima to conduction band minima, it needs change in energy and momentum, right? So that's the reason it's an indirect band gap semiconductor. Gallium arsenide on the other side, the gallium arsenide is a direct band gap semiconductor because the conduction band minima and the valence band minima, both of these are at the center of the Brillouin zone at k equal 0 point, right? So gallium arsenide is a direct band gap semiconductor. Anyway, so in the right hand side here, so I just plotted the ek diagram only in 100 direction. So if you see, so if you, this part is 100, right? So this part is 100 direction. So if you take the mirror image, so you could because we could have the ek diagram only in 100 direction. So here, this is the bottom of the conduction band in the positive K, and this is the bottom of the conduction band in the negative case, because these are mirror image of each other. So electrons can only be found at the bottom of the conduction band, because see, there are energy states here, right? So here there are energy states, right? So electrons will be any of these energy states, right? But mostly because electrons like to have at the minimum energy level, so they are found at the bottom of the conduction band. So since they are mostly accumulated at the bottom of the conduction band, so their effective mass, right? Effective mass is nothing but the slope of the curvature of the bottom of the conduction band, right? So, and similarly, the holes are found at the um, top of the valence band. So basically, holes are concentrated at the top of the valence band. And if you want to find the effective mass of holes, then you have to look at the curvature at the top of the valence band, right? And near the valence band maxima. Okay, so these things means we discussed, now we understand. Means I have not gone in very detail, but means whatever information we have discussed, this is more than sufficient for this course, right? Okay, but we are interested in number of electrons because when we'll talk about uh, electron devices like diodes, transistors, so we we will talk about electrons and holes, right? So basically we are interested in how, let's say I have a silicon crystal, I have take a silicon crystal, how many electrons and how many holes are there, right? Because the electrons, holes are the carriers for the conduction, right? Right. So if we want to find the IV characteristic, current voltage characteristic, we need to know the number of electrons, number of holes available. So for this, we need some more information. Need more information, and the first information we need is let me write. The first information we need is available energy states, right? Because the electrons will be available in the energy states, right? And so basically we need these available energy states, and how are these energy states distributed, right? So this is the first information we need. So when I talk about energy state, right? So I am talking about these lines that I have drawn here, right? So basically I know, okay, the electrons are at the bottom of the conduction band, but the electrons always occupy at a particular energy level, right? So there are energy states. So if there are no energy states, means we cannot have any electrons, right? So so since we are interested in the finding the number of electrons, and we are interested in the electrons in the conduction band, we are not interested in the electrons in the valence band, because valence band has electrons also, right? But we are not interested in this because the electrons in the valence band, they do not contribute uh, they do not contribute to the transport, right? The current, right? So, so basically, when we're talking about electrons and holes, we are talking about electrons in the conduction band and holes in the valence band, right? So, the first information that we need is available energy states, because in the conduction band, and mostly we're interested available energy states at the bottom of the conduction band, right? Because most of the electrons are there in the bottom of the conduction band, and how these energy states uh, are distributed at the bottom of the conduction band, and this will give us something called density of states. This is nothing but number of energy states per volume, because this is a 3D crystal, so per volume per energy, right? So basically because let's say if you take this is E, so if you take, let's say, DE kind of let's say DE energy state, DE energy, so little bit delta E, let's say delta E. So in that delta E, how much energy states are available? So the states per let's say unit, the number of energy states is nothing but uh, per centimeter cube per electron volt, right? If the volume is means if the dimension is in the centimeter. And the second information is the probability that these states are occupied, right? So what is the probability that these states are occupied? Uh, because even if we have states, right? It's not necessary that number of electrons is equal to number of states, right? Number of energy states, right? So there might be energy states, but if these energy states are empty, then that means we do not have any electrons, right? So let's say all the energy states in the conduction bands are empty. That means we have no electrons in the conduction band, right? So so we have to find density of states, but another information we need is probability that these states are occupied, right? So what is the probability? And this is mostly defined by something called Fermi-Dirac statistics, right? And we'll discuss that. Okay, so coming back to the states, so if I tell, okay, the number of states, because the states we have seen, we have, when we solved um, the Schrodinger's equation for a free electron in a potential well, right? We have also seen that these energy states are not uniformly distributed, right? So that's why so we have this states as a function of energy, right? So let's say number of states as a function of energy. So this is the density, right? Density of states as a function of energy. So we will not derive that. I will just mention. Uh, so I mean, so you could get it from the book. You could also derive, but it's not necessary in this course. Um, so let me write down the equation. So number of the density of states in the conduction band is when you calculate, because this is mostly given by this equation. So here a couple of things I just want to tell you. So one is this parameter here, right? So this is the density of states effective mass, right? But here, so density of states effective mass, because you see, when we discussed, right, silicon um, is anisotropic, right? So basically, it has different effective mass in different directions. So so the density of states will also be different, but this is the means. But we have taken this into account. So means we have in the longitudinal direction, transport direction, so effective mass. So but this is um, uh, just consolidated to this effective mass, which we call it density of state effective mass. And so here m star DSE is the density of states effective mass of in the conduction band, right? um, H, you know, Planck's constant, and E minus EC, because here you see EC is the bottom of the conduction band, right? So basically, if you see the EC here, this is EC is the this is nothing but conduction band minima, right? That energy level we called EC. This is the bottom of the conduction band, right? So basically electrons, so when you talk about states, right? So basically the energy will increase from EC, because let's say this is my conduction band, right? If this is my conduction band and the bottom of the conduction band is EC and top of the conduction band, let's say conduction band top, right? And this and right, and energy states, we want to find out the energy states in this energy band. So that's the reason, since EC is the reference, because bottom of the conduction band. So that's the reason we have E minus EC coming into picture here, right? So this E minus EC is nothing but your kinetic energy of electron, right? So basically, when the electrons, so electrons are at the bottom of the conduction band here, right? So and if you increase the energy of the electron, the energy electrons will move to the towards the top, right? So uh, they'll move towards the top of the conduction band, right? That means the kinetic energy increases, right? Um, anyway, so another thing here in many means you see that we have to multiply by a factor of degeneracy. Means basically this is I told you, right, when we're talking last class we talked about, right? So basically there are so basic so what does it show? Because you so see, this is my valley, right? So this is the valley of the conduction band, right? And this happens very close to the 1G0 phase of the silicon, right? In very close to the X point, right? So and we have 6 100 phases in silicon crystal, right? I mean unit cell. If you look at the unit cell, or there are 6 phases. So if you could imagine from the 3D point of view, there are 6 such valleys, right? So so this is, there are 6 such valleys. So we have to multiply by a factor g, which is 6 here, right? And similarly for um, germanium, right? So when we have to, the factor of degeneracy is 8, right? Because we have 8 such valleys, because it happens in 1 1 1 direction, right? So in the if you look at our last class, if you remember, so in case of germanium, the bottom of the conduction band happens in near to the L, right? L point, right? That is called L valley, right? And we have we have 8 L valleys in germanium, right? But in, so that's why the G will be 8 here. Again for gallium arsenide, uh, the bottom of the conduction band at K equal to 0, and that is the center of the Billon zone, we call the gamma valley. So basically in gallium arsenide, so your degeneracy factor is 1, right? Because we have only one valley, and that is at the gamma point, right? So uh, I'll not go in detail, because I mean, so I could spend a full day discussing about from where this equation come from, but it's not necessary for this course. So you just remember, so what is the equation uh, for the density of states, and this is only for the 3D crystal, right? So this is not for the 2D crystal. So this is for the 3D crystal. This derivation, and whatever you see here, the density of states as a function of E, this equation is only valid for 3D crystal. For the 2D crystal, it is different, right? For the 2D, right? Okay. So now, what does this mean, right? So basically, if you, I could write down. So if you see the first part here, so this part full, this is the constant, right? Because if you see the density of state, effective mass, h bar, the pi, g, these are all constants, right? So you could write this SE, the density of states, um, AC means a constant into root over E minus EC, right? So if you want to plot, right? So basically, if you plot, right? So let's say as you go on increasing the energy, basically you are increasing the kinetic energy of electron, right? So see, what do you mean by energy? So this is very important point, right? So we'll come to this point again and again, right? In the, when we're discussing transistors. So basically, when you increase E, that means bottom of the conduction band is the reference, right? So when you're going towards the top of the conduction band, that means that you are increasing the kinetic energy of electrons, right? You're not increasing the potential energy of electrons. You're just increasing the kinetic energy of electrons, because to move, then it needs certain momentum, right? So see, uh, this is my reference, right? So I'm not, so this electron here has also some momentum, right? But this is the reference momentum, right? Now if I want to increase my energy, when I talk about the increase energy of the electron is increasing, that means the electrons are gaining momentum, and they're moving in the to the top of the conduction band along the energy states, right? So basically, so this is the kinetic energy, right? So if you increase the energy of the electrons, so if I plot here the DOS, the density of states, right? This is also a function of energy. So because, okay, density of states, then you'll see this is root over E. So if you plot, this will be something root over E, right? So it will look like this, right? Uh, right. So okay. So all right. So this is how it will do at E equal to E. So this is E. So at when E equal to EC, so density of states is 0, right? Okay. So so now if I have my but basically the energy means we always plot in the vertical direction, because EK diagram, energy in the vertical direction. So basically if this is the bottom of the conduction band here, right? So if you are going towards the top, that means your density of states, if you plot, right, with energy, because uh, this is where the energy is increased, right, because this is the bottom of the conduction band, you see bottom, right? So as you go on increasing the energy, so your energy states will vary like this, right? So what does this tell physically is that as you go on increasing the energy, so density of states is increasing, right? Because this is see, this is SC is proportional to root over E, right? As you go on increasing, this SC will also increase. That means the you will find as you go on increasing the energy, you will find more and more energy states, right? So density of energy states is higher at the top of, means when you move towards the top of the conduction band. At the bottom of the conduction band, density of states is low, right? Okay, so this is a very important point. Please keep it in mind. We'll come back to this point while discussing devices, right? Transistors.
Sir, excuse me, sir.
Yes, Monica.
Sir, in this EC would be denoting the potential energy then.
Yes, I mean, so the electron. No, no, no. This is C. Okay, so if you take the EC as the reference, right? So as I told you, right? So potential energy, that means if the kinetic energy is zero, that means K equal to zero, right? But imagining, since the electrons, imagining this, the EC means bottom of the EC, right? So this is the reference. Then you could imagine, okay, EC is the potential energy, right? So that is the reference. So we started with this, whatever energy of the electron there, that is the potential energy, then because that is my reference, right? Then if if you give electrons more energy in any form, like heat or light or whatever form, so then they will move to the top of the conduction band, then that means they are gaining kinetic energy, right? So basically they have some additional energy with respect to the bottom of the conduction band, and that additional energy we call that kinetic energy, right? So in that way, EC is the potential energy. Yes.
Okay, sir. So, sir, according to the statement that you gave that S of E is equals to K under of E minus EC, if energy is zero here, like in this diagram as you drew, like
The
DO
energy is
is
not zero, so basically you cannot have E equal to zero, right? Minimum is E equal to EC, right?
okay, okay, fine, take it. Okay, sir.
Yeah. Because we cannot go below EC, right? So EC is our reference, right? Huh.
Okay, okay, yes, yes.
Sir, in case of gallium arsenide, it is direct band gap.
Yes.
So the minimum, it has minimum, it is in conduction band, it is minimum, like the electrons are in lower energy
Yeah,
level.
at K equal to zero, so their conduction band minima is at K equal to zero, and K equal to 0 point is the center of the Brillouin zone. So your minima and valence band maximum both are happening at K equal to 0 point.
So in this kinetic energy will be zero then.
K equal to 0 means if the crystal momentum is zero, that means the kinetic energy is zero, right?
Okay.
Right. See, uh, means from the classical mechanics point of view also, if your momentum is zero, that means particle means whatever is not moving, right? Object is not moving, right? So it's not moving, whatever energy it has is the potential energy, right?
So, sir, so like here we can say that in case of indirect band gap, at initial only, like at conduction band minima only, the particles will have some kinetic energy because they
They
have a
have some momentum, right? So that's right,
yes,
right? But since we're taking that as reference, right? That is the reference energy the electron has, right? Right?
hmm.
Because that is the bottom of the conduction band, and we are taking the bottom of the conduction band as the reference in all our calculations. So then whatever energy they are, then I am assuming that this is the potential, that is the potential energy of the electron, right? But
Yes,
if you see from the EK diagram point of view, because K is not zero, right? K is
yes,
finite. That means in basically the electron has some kind of energy, right?
yes,
But in our calculation we are taking that, okay, EC is our reference. So whatever
hmm.
energy electrons have at the bottom of the conduction band, if you take that energy as the reference, then whatever energy the electrons are gaining, then that energy E minus EC, I'll tell it kinetic energy of the electron.
Yes, sir. Got it.
Because the electrons will be at rest, and so we are assuming that electrons will be at rest at the bottom of the conduction band, right? Okay, so so this is means we have to multiply, means we have this G factor because we have 6 different values in silicon. But for germanium we have 8 different values, and for gallium arsenide, indium gallium arsenide, or indium arsenide. So for all those cases, the K means the uh, uh, the conduction band minima and maximum happens at K equal 0 point, and they have only one value, gamma value, right? Um, okay. Um, so similarly, we have also means density of states in the valence band, and it comes with the same equation. Uh, but here you have to take the density of states for holes and not the electrons, because we are interested in the uh, holes part, right? Valence band, I mean holes in the valence band, right? And here we don't have to multiply 6, because if you see there is basically there is one value, valence band value is the same, right? For this is uh, the density of states in the valence band, right? Okay, so then means okay, now we understand the density of states. That means these are the energy states available, as I gave you example earlier, right? If you think for a class point of view, this will just give you how many chairs are there in the class, right? But this will not give you how many students are there. If I'm interested in the number of students, in this case we are interested in the number of electrons and number of holes. So this will not give you any information about number of electrons. These are the energy states available, right? But these energy states, whether they're occupied or not occupied, we don't know, right? And so this occupancy, the probability of occupation is more defined by something called the Fermi-Dirac statistics, and you might have means this is a very common function. Um, so all of you who has done electronic devices at some point might have come across this equation. So this is called the Fermi. Um, this is the Fermi-Dirac probability function, right? So Fermi-Dirac probability function. So this just gives you the means um, so this just tells you what is the probability that a particular energy state is occupied, right? So think of from the class analogy, right? So basically we have chairs, right? Chairs are nothing but energy states, right? So these energy states can be occupied, right? So these energy states will give you what is the maximum number of students we can have, right? See, if uh, all the chairs are filled, right? That means the number of students in that class is number of chairs, right? But it's not necessary that at certain point of time all the chairs will be filled, right? So to find the number of students, we have to see what is the number of chairs into the probability that the chairs are filled, right? Or the statistics probability, right? So similarly, if you know the density of states, we know now the density of states, right? For silicon crystal, we know the density of states, right? Right. So these are the energy states available, right? Now, this the Fermi-Dirac probability function will give you what is the probability that these energy states are filled, right? So here means E is the energy, right? So E is the energy, and EF is this is basically a reference energy, popularly called as Fermi level. Reference energy, we call it Fermi level, right? Fermi energy level, right? Right. So okay, so this is a very interesting function. So let's say let me write down 1 by 1 plus p to the power e minus ef by kt, right? So basically, if I take EF as the reference energy, so let's say if I plot it, this function means most of you have seen the plot, but let me reiterate the things here. So I told you, right, EF is my reference energy. So let's say EF is my reference energy here, right? So if at absolute zero, that means temperature means absolute zero temperature, T equal to 0 Kelvin, right? At absolute zero temperature. So if I go, if E is greater than EF and E is less than EF, right? So EF is the reference energy, and so don't think about what is that reference energy, but let's say your your energy is more than EF or energy is less than EF. That means in this case E minus EF is positive, right? And in this case E minus EF is negative, basically, right? Right. Okay. So if you see here, so if T equal to 0 and E minus EF is positive, right? That means E to the power positive infinite means basically you could think of, right? So E minus EF is positive divided by 0. So this is E to the infinite. So, and Fe will be 1 by infinite. This will be 0, right? So this is how this is defined. So basically this part, your probability Fe will be 0 because E minus EF is positive, right? And if E minus EF is negative, so basically E to the power minus infinite you could think of, right? So then then uh, this will be 0. So 1 by 1, this will be 1, right? So this is how the this function, if you plot, uh, but there will be discontinuity here, right? So basically, so basically, how will you do that? So you have to take E minus EF equal to plus delta, right? Or E minus EF equal to minus delta, right? Otherwise, it will be very difficult, right? Right. So if E minus EF is plus delta, then this will be plus infinite. If E minus EF is minus delta, this will be minus infinite, right? So but when E equal to EF, right? When E equal to EF, so this function is half, right? So this is um, so FEF is half, right? So FEF is half. So this is basically 1, this is 0, and this one is half, right here, right? So what does this tell you? The probability that energy state is filled at E equal to EF, right? So then let's say that energy state is right at EF for the reference energy level, then the probability is half. If you go above that, probability is 0. If you go below that, the probability is 1. That is at absolute zero temperature, right? I'm talking about absolute zero temperature, right? So what does it tell? That so if the energy, so probability uh, probability of occupation is 0 if that energy is above Fermi level, and probability of occupation is 1, that is 100% if the that energy is below Fermi level, right? So Fermi is a reference energy level, right? Okay. So now if you increase temperature, so basically this is at T equal to 0 K, right? But if you if T equal finite, not 0 Kelvin, then you will see that this I mean, I could plot it. So means you have already seen, so I don't think it will surprise you. So you can have a plot like this, right? So basically this is for T equal to 0 Kelvin, and this is some, let's say T equal to some greater than 0 Kelvin, right? So your plot will change like this. So what does this tell you? So if you go above absolute zero temperature, right, above T equal to 0, so um, this Fe, the shape of this function, the graph will change, right? So there is a finite probability that energy states above EF can be occupied, right? These energy states, there is a finite probability, right? And these energy states are not 100% filled, right? So okay, so this is the Fermi function, right? So I mean, all of you have seen, so I don't think you will have any question here, uh, right? uh, but another thing is, Fe, let me write down 1 plus E minus EF by KT. But here also we do some approximation. Let's say if E minus EF is more than 3 KT or 3 to 4 KT, right? Right. So that means this we could write this Fe as one. So basically, e to the power minus e minus ef by kt, because if e minus ef is greater than 3 kt, that means this will be e to the power 3, and e to the power 3 is generally much higher than 1, right? So then this will be e to the power minus a minus kt, and this approximation we call it Boltzmann's approximation, right? And Boltzmann's approximation. This is a simplify, because basically means uh, we need simplification, because when you so we'll see that the Fermi function is very difficult to handle, right? So this function, so there is some approximation. So approximation is if we are only interested in energy levels, probability of energy states 3 kt above the EF, right? So that means we could then E minus EF becomes 3 kt or more than 3 kt. Then one we could neglect, this one will neglect, and this one will neglect, then it will be either minus C minus F kt, and this is called Boltzmann's approximation. Okay, so now we know the density of states, we know the probability density, the probability function, right? So if I want to find the number of electrons in E, right? So then the states, basically this will be nothing but um, okay, so so what I have to multiply, so basically I have to multiply the density of states SC. So the unit is per centimeter cube for EV, and this probability function, this do not have any unit, so no unit here, right? So now, so what does it tell? Basically let me draw. So if this is your conduction band, and we are interested in the there are density of states, right? Basically means if equation tells you that as you go to the top, then it will become more dense, right? So basically you could draw it, right? So if I take let's say if you find the number of electron, if I take only, okay, let's say I am only interested in this part, right? And this is DE, this part is DE, that means this is the bottom of the conduction band EC, this is EC plus DE or delta E, right? So then the number of electrons between EC and EC delta E, so that will be nothing but, let me write down, so states into Fe into del, right? So right, then this is how then you will get the number of electrons per volume, right? So if you want to find the total number, because we are interested in the number of electrons in the conduction band, right? So if you want to find the total number of electrons in conduction band, we call it N0, right? Total number of electrons, and 0 is the intrinsic, right? So basically or N, right? So let's not confuse you here. So let's say the total number of electrons in the conduction band N, then we have to do bottom of the conduction band EC, bottom or EC to the top of the conduction band, right? And we have to do the integration, right? So Fe times D, right? So this is what will give you the total number of electrons in the conduction band. But since so we know the EC, right? But we don't know the EC top, right? So what is the top of the conduction band means we don't know, right? So here there is another approximation. This EC top is removed, means replaced by infinite, by assuming that, see, as you go to the top of the conduction band, as you moving from the bottom to the top, right? So the probability of occupation is also reducing, right? Because the Fermi function is exponential function, right? So bottom of the conduction band se upar ja rahe ho, that means Fermi function means this is reducing exponential, right? So even if you replace EC top by infinite, you are not inducing much error, right? You are not adding much error, because anyway EC top say infinite, there will be very less number of electrons. The probability will be very less, right? Because Fermi function that is reducing exponentially from the exponentially, right? When you go on increasing the energy, right? So this is a fair, because but it will make your mathematics simpler. That's the reason EC top is replaced by infinite, right? If you do that, I mean, this will be. Let me write down. So you have AC. Let me AC, FE, DE, and you're going from EC to infinite. And so your AC is nothing but we have written this function h bar square root over E minus EC times 1 by 1 plus e to the power minus E by EF by KT Fermi function into D. Right, so this is how it will look like. Now this is EC to infinite. So this, because this EC top is replaced by infinite here, so this it is easily solvable mathematics, right? So if you do this math, I mean, so I'll just write down. I mean, because these are see, you see these are constants, right? So you could take it out, and means we will not do the math. You could find in any popular books this mathematics. So basically, I'll just write down the final equation. This is the equation of electrons. So your n right. So so your n here will be some constant, and that is called the effective density of states. Um, so okay, so I don't remember what is the formula. Let me look at my notes. So the effective density of states, yeah. So here, I mean, if you effective density of states will be 2g m star DAC KT divided by 2 pi h bar square to the power 3 by 2, right? So if you, so basically this is your this is called the effective density of states, right? So effective density of states. So this is the effective density of states in the conduction band, right? So effective density of states in the conduction band. Similarly, you could find the hole. So to find the hole, concentration of hole, so then you have to take okay, so from the top of the valence band to the bottom of the valence band, right? So basically, or we could also do, right? This is fine. EV bottom to EV top, right? So here, then you know the states, energy states in the valence band SC, but here we are talking about holes, right? So if the probability that one energy state is occupied is Fe, the probability that energy state is empty. So hole is nothing but that energy state is empty, right? If the energy state is filled, that means we have electron there. The energy state is empty means we have a hole there, right? There is no means absence of electron, right? So this will be 1 minus Fe here, and here DE, right? So then if you solve, and again, so EV bottom you have to take infinite, because we have to go from infinite to EV. So so this you could replace infinite to EV here, right? So if you solve this, then it will be NV e to the power EV minus EF by KT, right? And your NV you could also write down. I mean, NV is 2 m star density of effective mass KT divided by 2 pi h bar square. Right. Okay. This is how the electrons holes are calculated. So this is see basically how do you do it? So basically you have to find the energy states. So we first, okay, how many energy states are available in the conduction band? Then what is the probability that these energy states are occupied? Then we multiply both of them and take integration, right? So so this will give you the number of electrons in the conduction band and number of holes in the valence band, right? So let's say um, if there is no electrons in the conduction band, that means there will be no holes in the valence band. See, so basically, let's say, so what you tell, the valence band is filled, right, and conduction band is empty, right? So if let's say there is an energy state where there is an electron in the conduction valence band, right, and if that electron by any means goes to the conduction band, right, so it leaves behind empty states, because empty states means that that state was earlier filled, right? Now that was empty, right? That means we have a hole there, right? And electron goes to the conduction band, we have an electron, right? So for a typical semiconductor, we call it intrinsic semiconductor. It means your silicon crystal is an intrinsic semiconductor, right? Intrinsic means there are no defects, it's not doped, nothing, right? So it's an intrinsic, pure semiconductor, right? For a pure semiconductor, we are still discussing about the pure semiconductor, right? So for a pure semiconductor, the number of electrons in the valence band, number of holes in the valence band is equal to number of electrons in the conduction band, because absolute zero temperature conduction band there are no electrons, and valence band we can have only electrons, right? So if let's say if you increase temperature, the electrons gain energy and they go from valence band to conduction band, then they leave behind holes, right? So let's say one energy state is filled in the valence band, now the electrons go to the conduction band, there is no electrons, that state is called hole, right? That means we have a hole there, right? So these electrons can come back to that energy state, right? Okay. Similarly, if you flash light on the semiconductor, so the electrons in the valence band can go energy, can get energy and enough energy, so they could go from valence band to conduction band, right? So and they'll leave behind electrons, right? So leave behind holes, right? So basically, the number of electrons in the valence band is always equal to number of electrons in the conduction band for an intrinsic semiconductor, right? So here, if you your n is nothing but the number of electrons in intrinsic semiconductor, right? Because we are still talking about pure crystal. We are not talking about that your semiconductor has we have created defects or created means introduced doping in it, right? That's why this is called N0, because this is a pure semiconductor, N0, and or let me stick with n. Then if you multiply n into p, right, in this equation, so I have derived n and p, so that will be nc times nv. So this is e to the power minus ec plus ef plus ev minus ef by kt, right? So then this will be nc nv. So your ef will cancel, so this is ev minus ec by kt, right? So your valence band minus conduction band, this is nothing but your energy, so nc nv e to the minus eg by kt, right? So okay, so basically okay, so so here as I told you, so for intrinsic semiconductor, the n equal to p, right? So I think all of you understand that there should not be any question here, because for intrinsic semiconductor, if you find electrons in the conduction band, that means those electrons are coming from the valence band, because at absolute zero there is no means this is how the bands are defined, right? Conduction band, we do not have any electrons. If you at some point of time if you find electrons, that means these electrons are coming from the valence band, right? So number of holes in the valence band will always be equal to number of electrons in the conduction band, and that's why we call it the intrinsic concentration of electron, right? or intrinsic concentration of holes, right? And we could call it Ni square, right? N equal to P equal to Ni, right? So then this Np will be Ni square. So this Ni square is nothing but intrinsic concentration of electrons or holes. This will be NcNb e to the power minus Ag by Kt, or your intrinsic concentration is nothing but root over NcNb e to the power minus Eg by 2 Kt, right? Right. So this is your Ni. So this is the intrinsic concentration of electrons, and see the intrinsic concentration of electron depends on band gap, right? So if your band gap is low, that means there is more probability that that electron can go from valence band to conduction band, because this less gap between energy difference between conduction and valence band. If they're very close to each other, so electrons, a little bit thermal energy or some energy from external sources, the electrons can go to the conduction band from valence band, right? So that's the reason there is more probability that you'll find, there is possibility that you'll find more electron in the conduction band at a certain point of time, right? So that's the reason your Ni is a function, is e to the minus Eg, right? As you reduce your band gap, your Ni will increase, right? So so the Ni, sorry, your Ni in germanium is more than Ni in silicon, right? And Ni in silicon is more than Ni in gallium arsenide, because gallium arsenide, this has a band gap of 0.66 eV, this has a band gap of 1.12 eV, and this has a band gap of 1.42 eV, right? So Ni of germanium is much higher than, I mean, almost, you see, basically this is around 10 to the 3 times higher, right? So germanium intrinsic concentration is 1,000 times higher than the silicon, and similarly gallium arsenide has 1,000 times lower than, almost 1,000 times lower than silicon, right? So so intrinsic concentration is, if your crystal is pure, your pure semiconductor, this is the number of electrons and holes, right, at a particular, because we deal with room temperature, right? Basically absolute zero, there is no electrons in the conduction band. Since room temperature, this is room temperature, we have some electrons, and that is defined as the intrinsic concentration, right? And similarly, if you go on increasing temperature, your intrinsic concentration will increase, because if you go on increasing temperature, then the more of the electrons will come from the valence band to conduction band, because they will get thermal energy Kt by Q, right? So this, because of this thermal energy Kt, so electrons can get that Kt, so they can come from the, go from the valence band to conduction band, right? So with increasing temperature, the intrinsic carrier concentration will increase. That means the number of electrons in the conduction band and number of holes in the valence band, both will increase similarly, right? Okay, and similarly with the light, right? So if you flash light, right, your intrinsic concentration will increase, right? And that means number of electrons in the conduction band will increase, as well as number of holes in the valence band will also increase. Right? Okay, so okay, so then it's basically so means I think we have only 2-3 minutes left. I don't want to go jump to the next part of the course, but I'll just give you some information here. So let's say indium arsenide. Indium arsenide has a band gap of almost 0.3 electron volt, and silicon has a band gap, let's say, have around 1.12 electron volt, right? So right, so at room temperature, right, so which semiconductor has more number of electrons? So concentration of electrons is higher in silicon or indium arsenide?
Sir, can you repeat what is the question?
So indium arsenide has a band gap of around 0.3 electron volt, and silicon has a band gap of 1.12 electron volt. So at room temperature, which semiconductor, which of these material will have higher electron concentration? At room temperature. Room temperature is,
Indium arsenide.
yeah, indium arsenide will have higher temperature. And let's say if I go on increasing temperature, right? So the electron concentration will increase in both the semiconductors, right? Which materials will have, means the increase in electron concentration, will it be same in both the semiconductors with temperature? Will it be same?
No, sir. In indium arsenide, it will be more because band gap is less, so number of electrons will more more go from valence band to conduction band.
Yeah, exactly, right. So basically, since indium arsenide has a lower band gap, so the increase in electron concentration, electron hole concentration in the conduction and valence band respectively will also be different with temperature, right? I mean, basically, it is more with temperature compared to silicon, right? And so this is from the temperature. So let's say if you want to build a temperature detector, right? So basically, let's say you want to have a sensor, means temperature sensor. So which metal will you use? Which metal will have higher sensitivity? So how you build a temperature sensor? Basically, the conductivity will change with temperature, right? Because as you go on increasing the temperature, the number of electrons will increase, and if the number of electrons holes will increase, the conductivity will decrease. So if you measure the conductivity, if you take a piece of silicon, measure the conductivity at different temperature. So this will, from there you could find the temperature, right? So if you build a temperature sensor with silicon and indium arsenide, which of these sensor will be better, and which of these sensor will be better? Will be a good sensor? Is a good.
Indium arsenide.
Why do you think indium arsenide is a good sensor?
Because it has the lower band gap, so it can sense means electrons will be transferred from valence to conduction at lower temperature also.
Okay, so okay means definitely the sensitivity is higher in indium arsenide compared to silicon, because with temperature the number of electrons will increase faster in indium arsenide compared to silicon, right? So conductivity, if you plot the conductivity with temperature, the slope is much higher in indium arsenide compared to silicon, right? But indium arsenide, I mean, basically the sensitivity, definitely the sensitivity will higher for the indium arsenide temperature sensor. But indium arsenide will also be very noisy, right? In the why I'm telling it will be very noisy, because since this is low band gap material, little bit change in temperature will change the conductivity by a large amount, right? So since the sensitivity will be lower, sensitivity is higher, uh, your sensor will be very less noisy, right? So any spurious signal it will also pick up, right? So so you have to take care of that, right? So only sensitivity is not the only thing. So you also take care of how your sensor is robust to noise, right? Yeah, so you could think about it. And similarly, because of the different band gap, so these materials are used for if you use it in the photo detector, so they're used to detect different wavelength light. So silicon is mostly, I mean, silicon is not a very good photo detector because it has indirect band gap material, right? But if you talk about indium arsenide is a direct band gap material, right? And indium arsenide being a lower band gap, so it could detect higher wavelength lights, right? Uh, so I mean, basically, if you want to go to infrared or far infrared, right, higher than infrared detection, then you have to go to lower and lower band gap materials, right? And more lower to lower band gap materials also have less, I mean, high thermal noise because of lower band gap, right? So since they have very high thermal noise, so basically, if you want to use it as a photo detector, you have to use it as at lower temperature, right? Because it is very prone to thermal fluctuations, right? Because of lower band gap. That's the reason indium arsenide detectors, if you want to have a photo detector using indium arsenide, So you have to operate at a very low temperature so that this noise could be reduced, right? Thermal noise could be reduced. All right. So I think okay. So this is just some view. Means all right. So any questions here?
Sir, can you say about Fermi data, Fermi level little bit more? What it is means?